section we will learn about power of the lens. Means we have studied about convex lenses and concave lenses. Now we will learn about power. Now before telling you what is power, I would like to explain you certain phenomena here. Suppose I am taking here two convex lenses, one of lesser focal length and another with little larger focal length. We suppose this is my convex lens and this is the principal axis. This will be the focus, principal focus I will say. Suppose in this case my focal length is this distance between origin and focus is suppose 15 centimeter. Then if the rays are traveling parallel, definitely according to our condition they will get diverged, they will get converged at this focus, right? This was the first case. Now suppose this angle means the angle by which they get converged, I will say suppose it is I am writing as A1, that is angle. In the first case it is 60 degree. Now I am taking another convex lens of little larger focal length, suppose like this. Here now these are the foci. So again a parallel beam will incident on the lens and it will get refracted through the focus on other side. Now you can consider this angle again. Suppose the focal length was here 30 centimeter, means double of the first. Now you will measure the angle and you will find that this is the convex lens we are taking. If the focal length is shorter, light bends, means light rays through the large angles, means this angle will be less than 60 degree. If you want, you can draw at your notebook by taking different focal length but same size of lens here, and you will perform the experiment, means you will draw the diagram. You will always observe that if the size is, means focal length is of shorter size, then light rays bend to large angles, means bending will be more, no? Means this suppose this is the principal axis. If here is the focus, light will bend with this angle, and larger is the focus, means at longer distance focus is there, light will bend like this. So that means for the smaller focal length, light rays bend through larger angles, means we are talking bending from this side. So this angle will be larger here, and here you can see this angle is larger here and this angle is shorter here. So A1 is, suppose if I am taking this as A1 here, it will be 60 degree, and suppose if I am taking A to here, this will be less than 60. So this is the bending here. Now similar case will be applicable for concave lens. I will show you. Here is my concave lens. This is the principal axis. Here is origin. Again here, focal length is suppose 10 cm. Parallel rays will incident and they will look like they are diverged from the focus like this. So you can see here will be the angle of divergence. Suppose it is A1. You can see it is very smaller. Suppose it is 40 degree. Now suppose similar lenses I am taking here. Now my focus is at longer distance. Suppose here focal length is 20 cm. So again light will fall parallel to the principal axis like this, and you can see it will appear that whether it is diverged from focus like this. Now you can compare both the angles. You will find it will be less than 40 degree, right? Because bending is from farther distance. So here I am saying the sentence again. For a convex lens of short focal length, light bends through large angles by focusing them closer to the optical center. You can see here the optical distance is means focus is closer, and here from the origin the focus is at a longer distance. And for a concave lens, a very short, means I will repeat, for a concave lens, a very short focal length causes higher divergence than the one with a longer focal length. Means here divergence caused by the short focal length is more. Means here angle will be greater here, and here you will say that the angle will be smaller here. That's why I have written less than. Means at smaller angle the divergence of the rays will takes place. So now why I am explaining this means the divergence, angle of divergences or angle of convergences will depend upon the focal length of the lens. So here we define a new quantity which is related to focal length. It is called power and it is denoted by P, and it is reciprocal of F. That is 1 upon focal length is the power of the lens. Now here I will explain you the examples. Firstly, the SI unit of the power is known as diopter. Means if I am saying the lens is of focal length plus 1 meter, that means its power will be definitely, it is 1 diopter per meter. So SI unit will be per meter, and it is known as diopter, and it is denoted by capital D. Means if focal length is plus 1 meter, then power will be plus 1, means 1 upon plus 1 diopter. So in this way you will write the power. Now how it is related? Remember, the numbers of the spectacles are mentioned in the powers of plus and minus. Means suppose I am saying, or eye specialist is giving the number by writing plus 2 power in both the eyes. That means the person will have to wear convex lens, because convex lenses have plus power and concave lenses have the negative power. Why is it so? Because you will remember, for the convex lenses, image is formed on the right hand side. That's why the distance of the image is always taken as positive and focus lies on the right hand side. That means power will be positive. And for the concave lenses, image is formed on left hand side, means on the same side of the object. That's why the focus which matter here is the focus which lies on the left hand side, that is f1. Means for the convex lenses f2 matters, for the convex lenses f1 matters. So that's why the power of the convex lenses is always positive, whereas the power of the concave lenses is always negative. Through the convex lenses you will observe the real images obviously, and through the concave lenses you will always observe the virtual images which are not real. Through the convex lenses, the image may formed enlarged or magnified. For the concave lenses, image formation may be diminished or enlarged depending upon the position of the object. So here the example I was telling you, so person wearing plus 2 power means actually he has to wear convex lens of power plus 2. That means the focal length will be opposite of that. It will be 1 upon. So accordingly the focal length of that lens will be calculated. So here we complete our chapter. We will solve exercise based on this chapter along with the numericals from your textbook.
No more spending your energy and money on coaching classes, or missing classes for rain, for rally, and any other nonsense. Subjects covered by multiple teachers with repeat telecasts. Doubts, concepts, applications, no problem. All explained through great and significant animation. So sit back comfortably in your home and watch Study Spectrum TV channel.
Let us solve exercise from your textbook. Now we will solve all the questions which are given in the exercise for your reference, so that it will easy to understand each and every question. So first question you have, which one of the following material cannot be used to make a lens? Now suppose this is a lens. You must remember that we had drawn the ray diagram for the lenses. Lenses allow, suppose this is the principal axis, lens allow the passage of light. Means light ray will come from one side and will get passed through the lens and will come on another side. So definitely for making lens we need transparent materials which will allow the pass of ray of light. So here we have 4 options: water, glass, plastic and clay. Out of 4, first 3 options, water, glass and plastic, are transparent materials. Even the transparent plastic is also available. For example, the glasses with fiber are known as, those are used for making spectacles, and also we have plastic prisms and all. So plastic is also transparent material here. So all the three materials which are mentioned in the first three options are transparent material, will allow the passage of the light through it, but clay will not do so. Clay is not a transparent material. So your answer is clay, and you will write that from the clay we cannot make the lens. So clay is the answer. Question number 2 is, the image formed by a concave mirror is observed to be virtual, erect and larger than the object. Where should be the position of the object? So in this case we have concave mirror, means we are not taking concave lens, it is concave mirror. So concave mirror will be like this. If you remember, we had studied 6 cases of image formation by changing the positions of the object. So here condition is that you have a concave mirror, and for this concave mirror, image formed is virtual image. Virtual image means it is not the real, so definitely it will form on the same side where the object is kept. It is erect, means like this we can say. Suppose this was the object, so this is the image. It is virtual, erect means straight, and larger, thus larger than the object, so that you can see. And accordingly, suppose AB was the object, and here A dash B dash is the image. We have to find the position of the object. So options are between the principal focus and center of the curvature, at the center of the curvature, third option beyond the center of the curvature, and fourth option between pole of the mirror and its principal focus. So if you remember, or if you will revise the all 6 cases, you will find that if we will place our object between the focus and pole, means here if we place our object, accordingly you will get the virtual, erect and enlarged image of the object. So your answer is fourth option, between the pole of the mirror and its principal focus. So between F and P you will place the object, and accordingly you will get the image here. Question number 3 is, where should an object be placed in front of a convex lens to get a real image of the size of the object? So let us see the case. We have convex lens here. Suppose this is the principal axis, x dash, x. Now in this case we have to place our object so that we will get real image, means definitely it will be on the other side. Secondly, size is also given, means image size must be similar to that of the object. So let us see, we have 4 options. First option, at the principal focus of the lens. Second option, at twice the focal length. Third option, at infinity. And last option D, between the optical center of the lens and its principal focus. So here your B option is correct. It is at twice the focal length, means I will show you how the image is formed and how the option is correct actually. Suppose these two are the foci and centers of curvature of the lens. Now we will place object here. Suppose it is A, B. Now accordingly we will draw the ray diagram. So you will find that your one ray will pass from focus and other ray will pass from the center, means origin of the lens, and accordingly at C2 you will get the lens. Now here actually I am drawing just randomly, that's why the image size is not equal to the object size. But if you will take correct distances and you will draw, you will find that you will get the image at the second curvature, center of the curvature, and it will be of the same size that of the object. For your reference, you can study the 6 cases that we had studied image formation by convex lenses. So we had 6 cases. By changing the positions of the object, we got the different sized images at different positions with different natures. So you can revise that. So your option B was the correct one. Question number 4 is a spherical mirror and a thin spherical lens have each of focal length minus 15 centimeter. The mirror and the lens are likely to be first both concave, second both convex, third the mirror is concave and the lens is convex, and last option is the mirror is convex but the lens is concave. Now if you remember, in the end of the chapter we had studied about power of the lenses. So in that section we studied that concave lenses have negative power. So one thing is clear, power lens is negative, so that will be definitely the concave. But now what about the mirror, the spherical mirror we are talking? So here option A is correct, because by convention the focal length of the concave mirror and a concave lens are taken negative, because we are keeping our object on either different sides, and on the same side we are getting the image in the case of concave mirror and concave lens. So hence both the spherical mirror and the thin spherical lenses are concave in nature. Mostly for convex mirrors and convex lenses the power is positive. Focal length is also taken as positive because object is formed on the different sides of the mirror or lens. Then we have next question, it is question number 5. No matter how far you stand from a mirror, your image appears erect. The mirror is likely to be, options are plane, concave, convex, or either plane or convex. Now very simple, you have a mirror and you are standing in front of you. Distance may change, and condition is that for all the distances image will be straight. So actually a convex mirror always gives a virtual and erect image which is smaller in size. So that's why option D is correct here. Either for a plane mirror we get the erect image, that is the Delhi phenomenon, we watch in the mirror and we got our image. So plane mirror is one option and second is convex. So answer is D here. A convex mirror always gives a virtual and erect image that is of the similar size of the object in front of it. Similarly, plane mirror does the same thing. The object which is in front of the plane mirror, image formed is also virtual, erect, and it is of the same size of that of the object. So D is your answer. The next question we have, it is question number 6. Which of the following lenses would you prefer to use while reading small letters found in a dictionary? This is very simple question that you must have performed or you must have seen. The pharmacist which is working in a medical, as you know, means on the medicines the letters are written are very smaller. So to read that the pharmacist use the magnifying glass. So you can see in the magnifying glasses both the surfaces are pointing outward or bulged outward. So that's why the surface which is bulging outward is definitely a convex lens. So let us see the option and accordingly we will answer. First option, a convex lens of focal length 50 cm, a concave lens of focal length 50 cm, a convex lens of focal length 5 cm, a concave lens of focal length 5 cm. Means actually you have 4 options. in the first option you have a convex lens of focal length 50 centimeter and again a convex lens of focal length 5 centimeter in the option C. Then a concave lens of a focal length 50 and again a concave lens of focal length 5. So as you know, smaller the focal length, greater will be the power of the lens. So definitely we have to consider the lens with lesser focal length. So either option C or D is correct. So here option C is correct because of convex lens, the image or the size that we are looking from it is magnified, means objects can be seen larger in size. So answer is C. A convex lens gives a magnified image of the object when it is placed between the radius of a curvature and the focal length. Also, magnification is much more for convex lens having shorter focal length, because if you remember, the power was 1 upon f, means lesser the focal length, greater the power, greater will be the magnification. So C is your answer. Let us move to our next question. We wish to obtain an erect image of an object using a concave mirror of focal length 15 centimeter. What will be the range of a distance of an object from the mirror? What is the nature of the image? Is the image larger or smaller than the object? Draw a ray diagram to show the image formation in this case. So this is a kind of problem also, and here you have to write your answer in a theoretical form. So let us write down the values. Now here range of the object is given as it is between 0 to 15 centimeter. Now we have to remember, actually we are taking a concave mirror, so image means erect image is formed when object is placed between the pole and focus, and obviously here the image formed will be virtual image. So let us see. Suppose this is the lens, concave mirror here we are taking. Then suppose this is the principal axis, here is your pole, here is your focus, and here is your center of curvature. So here we will place the object like this. Then you will see that one light ray will incident at pole. So whatever is the angle of incidence here, with the same angle it will get reflected in the same side. Then again one ray will travel like this. So, and since it is traveling through center of curvature, it will be back reflected like this. So here if we are extending the ray, here you will find that at some point both the rays will coincide each other and we will get image here. So suppose this was AB object, so we will get A dash B dash as the image. Hence we will write, we obtain means to obtain the image of object from a concave mirror of focal length 15 centimeter. The object must be placed anywhere between the pole and focus of the mirror. Image formed will be virtual. Virtual means it is formed beyond the beyond the mirror. So that's why it is virtual. It is not the real. We can see that image only inside the mirror, not on the screen. So this is virtual, erect, and magnified because it is larger in size than the object. So this is the ray diagram that you will draw. Then Next question we have, question number 8. Name the type of mirrors used in the following situations. First situation is given, headlights of a car. Now if you remember, we had done the uses of convex lenses, uses of concave lenses. So if you remember, concave lenses act as divergent lenses. Means, suppose this is the concave lens here. This is the principal axis. Then the rays which fall parallel on the lens get diverged like this. So, in order to have the larger surface of incident light, means in order to diverge the rays so that the fallen light will get extended by its range, we use concave lenses here. So options means for the headlights we will write that we will use a concave lens in order to increase the range of the light here. So here second option is side or rear view of the vehicle. So definitely in the uses of convex lenses, you must remember, on the convex lenses or on if we are using the convex mirror, we get the smaller image but the rear view, means so that the driver which is driving the vehicle can see the traffic behind it. So here we will use convex mirrors. Then third one, solar furnace. So here again we will use concave lens or concave mirror, I will say. Why? The solar furnace will get heated, means that will capture the light from the sun and it will transfer to the object, and definitely that light will get diverged so that it can means it will heat the object. So that's why in the solar furnace we use the concave lens or concave mirror. Let us solve next example. It is question number 9. It is, one half of a convex lens is covered with a black paper. Will this lens produce a complete image of the object? Verify your answer experimentally. Explain your observation. Now this is very simple example. See, we have a convex lens. Now there are two cases. We have to cover the convex lens by one half of its part. So we can cover like this, and also we can cover like this also. So let us consider the first case. In the first case, I have this convex lens here and we are covering it like this. Now suppose this is the principal axis. Here is your foci and center of curvature. Then suppose I am placing my object somewhere here. It is AB. Then now ray will not incident here. If it is incident, then also it will not get refracted. So what will happen? One ray will travel through focus and will incident on the half part of the lens here, and it will get refracted on other side like this, you can see. So one ray which is traveling through the focus will get refracted parallel to the principal axis, and suppose another ray randomly incidenting on the oblique direction on the lens, so it will get obliquely refracted like this or something, and accordingly you will see, you will get the image here. So it is A dash, it will be inverted image obviously, so it will be B dash and A dash here. So you can see definitely you will get the image, but in this way. Now let us study the second part when half of the lens is covered here. In the second part we can cover the lens from the bottom side also. So after this I will take that part. Suppose I am covering the lens. It is a case of first case, it is a case of first only, but I am covering the lens from the bottom side. So again, suppose this is the principal axis, x dash. Then we will place object here. The ray will travel and come from focus. Suppose F2 is here, and another ray will also travel and it will also get refracted on other side, and it will be cross the first ray and you will get the image here like this. So this will be again the inverted image, A dash, B dash here. So here we will say that in this case a ray of light coming from the object is refracted by the upper half of the lens. These rays meet the other side of the lens, form the image of the given object as shown in the figure. So in the next part, suppose I am taking the second case here, means covering the lens like this. You will see that the ray, incident ray will strike here, but because this portion is covered, this portion is not transparent, ray will not get refracted on the other side, so image will not form. So for the so you will write, if half part of the lens is covered vertically, the image will not form due to there is no scope of passage of a ray of light. So this is the answer. Now let us move toward next example. It is 10th example. An object 5 cm in length is held 25 cm away from a converging lens of focal length 10 cm. Draw a ray diagram and find the position, size and nature of the image formed. Now here the question is given about converging lens. So converging lens is actually convex lens. So let us do this question. It is given that object distance is 25 cm. So always we place our object on left hand side of the lens. So it is minus 25 cm. Then object distance, object height is given. The size of the object is given. So h is given. Since we are placing object vertically, means on the x-axis, so it will be plus 5 cm. Then again we have to find the size of the image, distance of the image and all. Focal length is given here. We will take the focal length as positive. Here we are using convex lens, right? So we can refer this figure also. For the convex lens, suppose I will complete this. This is the convex lens. If we are placing our object here, image will be formed on this side, somewhere like this. So it will be real image. So the focus that will matter is focus which is on the other side, that is right hand side of the mirror, means lens. So that's why the focal length we will take it as positive. So this becomes our data here. Now we have to find distance of the image and also the size of the object.